to the Disruptive Innovation Festival, or welcome back if you're joining us for another session. I'm Dale Walker, and joining me here in the Disruptive Innovation Festival studio is architect Michael Pawlyn, who is the founder of Exploration Architecture. Michael, in fact, is a regular guest here at the Disruptive Innovation Festival. He's joined us on a few occasions in the past. And today we're going to be chatting about computational design. So, Michael, I mentioned that you've been at the DIF before. In fact, you closed out the final session of the first Disruptive Innovation Festival in 2014. And I've actually got a quote that you said on stage at that session, which I'm going to read out to you now to jog your memory. You said, "Humans are actually a very ingenious species, and one of the very appealing things about the age that we are entering is that I think we'll see a massive reawakening of that ingenuity." So it's been 4 years since you said those words. Do you stand by them now today? Do you think that we've seen that reawakening happen already, or is it still yet to arrive?
Well, I mean, I wish we were seeing that reawakening happening much more quickly. And frustratingly, it's not happening anywhere near as quickly as it should be. And you know, the latest IPCC report was a real wake-up call. And I sincerely hope that will be a sort of driver of much more rapid action. Because, I mean, one of the bizarre things about the age we're in is that we have nearly all the solutions we need to shape a really positive future, and it's not happening at anywhere near the pace that it should be.
That's very well said, I think. And hopefully today, in the next 45 minutes, we'll be kind of addressing some of those topics. Before we dive straight into computational design, which I think could be quite a complex discussion coming up, I thought maybe we could take a moment to make sure that you and I and the audience online are speaking the same language. Okay, so sure. I studied engineering a few years ago now, and during that program spent a lot of time on software like SolidWorks or CATIA, where basically we've replaced the pencil and the ruler and we're doing our drawings, our technical drawings, our modeling on computer software, computer-aided design. Is that computational design? Is it fair to call that computational design?
I think it's worth making a distinction between the early versions of CAD or computer-aided design and the more recent forms of computational design. So when drawing first moved over to computers, it was a fairly direct translation. The computer was just doing what had previously been done with a pen or a pencil. The thinking was still being done by the humans. But the amazing thing about computational design is it really draws on much more of the computer's power. So a lot more of that logic and processing can be done by the computer. And that means that you can work through not just, say, tens of options, but literally tens of thousands of options. And by doing that, at least in principle, arrive at a much better all-round solution.
So is it fair to say that perhaps those kind of first uses of the computer to aid design were really not taking full advantage of the power that computers bring to us and that digitization can offer designers or architects every day, but whereas computerized design computational design is taking advantage of that?
Yeah, I think that's a fair way to summarize it, yeah.
So before we go any further, because I know we've got some examples to share of computational design in action, we've got a clip from a documentary that was produced for this year's Disruptive Innovation Festival. And I'd like to show that clip now. It features an architect by the name of Areti Marco Polo, who works as the academic lead at the Institute of Advanced Architecture in Catalonia. Okay. So let's see what she has to say in that documentary.
Now we are at a moment that there is a big change into how we design. Our designs, they are now being informed by parameters that until now, first of all, we didn't have access to, and second of all, we didn't have the manual or intellectual power to work with that, no? Computation is helping us to deal with a big amount of data. And this allows us to create designs that they are much more optimized and they are much more informed on parameters, from parameters that they are relevant to what we want to achieve. Sustainability parameters, environmental parameters, users' desires parameters, resources that surround what we construct. All those have been basically numbers that they were very difficult to manage to bring together into a design decision or into a design process.
So that was a clip from a documentary that's going to be released on the 15th of November called The System Reset. And Areti will actually be live in the DIF studio on the 22nd of November, so you can hear more from her there. Michael, she made 2 points in that clip that I'd like to chat about for a while. The first was a word that she used, this idea of parameters, and that computational design is giving us the ability to bring these parameters, sustainability parameters, environmental parameters, I think she said user needs parameters, into our design. What does she mean by parameters exactly?
Well, maybe a simpler way of putting it is the different aspects of performance that you want the building to meet, perhaps in terms of the amount of light you want in, the amount of external space you want for each residential unit, the access to sunlight, the proximity to transport nodes, that kind of thing. And often when you're designing, say, a new piece of city, you've got a lot of those different parameters that you're trying to optimize and form trade-offs between. And it's pretty difficult to do that by conventional means. I remember when I was a student, Sir Norman Foster was working on the design for the new BBC building. It wasn't actually built, there was a different version that was built. But I think his model shop made something like 100 different physical models. And everyone thought that was absolutely amazing, that they could go through that many options. But with computational design, and if you set the parameters that you want, you can work through literally thousands and thousands of options and arrive at something that has resolved the sort of trade-offs between a lot of those different ones that are potentially in conflict.
Okay, this reminds me of an article I was reading before this when I was trying to just kind of get my own head around what computational design is and what it offers. And it talked about kind of there being two elements to design, that there's the conceptual element of design where you're coming up with the ideas, you're kind of trying to meet the brief, and then the other element is the actual doing of it, the physical creation of models and testing. Yeah. And so what you're saying really is that part of the power of computational design now is the ability to rapidly, virtually kind of test almost an infinite number, or at least thousands of versions of the same design or slightly tweaked design to reach kind of the desired output. Is that?
Yeah. And one of the reasons it appeals to me is because it's getting closer to the way that biological evolution has worked. I mean, you could look at each organism as the result of a very long process of refinement according to a very complex set of parameters. And that has taken hundreds of millions of years. The great thing about computational design is you can compress that into maybe 1 or 2 days of powerful computing.
Brilliant. I'd like to turn to some examples that we chatted about in preparing for this session. The first one that I'd like to talk about is one where I think you said it was a water treatment facility or water treatment plant.
Right. Yes.
Okay, so we'll get that up on the screen now, and then you can maybe let us know kind of about the process that went into developing that and what it's all about.
Well, so this is quite a good one to start with because it just uses a couple of parameters, and it was inspired by this example from biology. So this branching system demonstrates what's referred to as Murray's law. Murray's law is a mathematical constant that appears to hold true for most branching systems in biology. There's a very constant ratio between the diameters of the parent vessel and the daughter vessels. And then there's also quite a constant angle at which the branching occurs. And then there's a certain finessing to those junctions. And overall, this appears to be an evolved optimum way of conducting gases and liquids around a biological organism. Mm-hmm. So we first used this to design a zero carbon data center. So instead of having the data blocks arranged in long straight runs, which would have had a lot of pipe work with a lot of 90-degree bends, we clustered them like this and then designed that branching system based on Murray's Law. And then we had an opportunity to take this a bit further. We were working on a tender for a massive new water treatment facility in the Middle East. And this was an existing facility. And you can see that it's all quite rectilinear. There's quite a lot of space between the elements. And when I first looked at that, I thought, well, that doesn't look like a great layout to me. And my colleague, who's an engineer, turned to me and said, well, isn't that rather arrogant of you as an architect to think you could improve on something that engineers have been working on for decades? And I said, well, hold on. It's not really about being arrogant. It's about being curious. And we knew that this tender was going to be determined partly based on the capital cost and partly based on 10 years running cost. Now, 10 years running cost for something as energy intensive as this is huge.
Yes.
So I suggested that we could use a biological or computational tool to try and optimize this. So my kind of grumpy colleague conceded that, yes, okay, if we could make a 1 or 2% saving in energy, then that would be worth having.
That sounds like something an engineer would be drawn to.
Well, I don't want to make any sweeping statements.
I studied engineering, so I feel like I can comment on
Okay. So one of my colleagues in the office developed this little tool. So this shows a hypothetical layout. The white circles are pieces of equipment, and then you've got a pipe layout that connects them. And what the tool does is it works out the optimum relative positioning of the pieces of equipment, the white circles, and it also optimizes the branching angle according to Murray's Law. And the figures at the bottom there, you can see that the total length of pipework came down from 100 to just below 64. And then we took that a step further. This one starts in a few moments. This was a completely accurate sequence of equipment for a proper water treatment facility, all in the right form. And this time we combined the figures for length and angle. Each bend you put into a system adds a certain amount of equivalent length in terms of friction. So that figure of total equivalent length is a very good measure of the amount of friction in the system and therefore the amount of energy required. And you can see that here we came down to well below 40% of the starting point. The eventual layout is not quite as aesthetically appealing, but this is a functional tool.
Yeah.
So you can see from that we could learn a lot from taking lessons from biology combined with computational design to arrive at a much more refined and efficient layout.
I mean, it certainly seems like incredible savings, and it is fascinating to see that original image you showed of the leaf and that organic form and how the computer, I suppose, has taken that very kind of grid rectilinear layout and created what, to my eyes, looks like an organic, kind of biologically inspired, certainly, shape. I'm interested, just to bring back the sort of words that Areti used in her clip, this idea of parameters.
Yes.
In this example, what would have been the parameters, say, that you were inputting into the simulation?
It would have been minimizing pipe length, optimizing angle, and I think that was it. So this was really quite a simple one. It was just those two main parameters.
And then the computer system or the algorithm has been designed to kind of optimize for those and adjust the shape or the design of the layout to do that.
Yeah.
The other thing that Areti mentioned in the clip there was kind of a bit of a bigger picture statement, which was that computational design is resulting in kind of a monumental or a big shift in how we design. How is it impacting your design process?
Yeah.
So the way that you go about kind of from concept or first discussion with a client, where does this fit into your process right through to kind of delivery of the final solution?
Well, it's good to do this fairly early on because this is pretty strategic, the kind of results that it produces. Sometimes we do this alongside a more conventional way of working. So for instance, we did a scheme called the Biomimetic Office, and we used fairly conventional design approaches, albeit using biomimicry as a source of ideas, alongside a computational approach that generated thousands and thousands of variations which were tested against the parameters. And interestingly, we found very similar results coming out of each. But one thing you need to remember is that with architecture, you can't necessarily define everything. Some people feel a bit nervous about these sort of tools. Is everything going to be overtaken by robots? And actually, there are certain aspects to architecture that I think would be very difficult to do computationally. Yes. So, cultural aspects or psychological aspects, such as what does it feel like to be in this atrium of a particular shape? And so we didn't necessarily accept everything that the computational tool suggested was optimum. No. We introduced some other. Well, we used a certain amount of judgment in deciding what to take from it.
I'm glad you raised that point, because it's one I want to return to a little bit later in the discussion. In the meantime, we've had a question through from the audience, the first one from Ronald, who asks, who needs to be convinced so that these flow optimizations, these computational designs can be used? To what extent is it easy to reverse engineer kind of right-angled existing designs? So two questions in there. Let's take the first one. Who do you need to convince that it's worthwhile?
Well, the people you need to convince really are the ones who are involved in designing new systems from scratch. It's actually pretty difficult to retrofit this because there's so many of the pieces are already there, so many constraints already exist, and it's quite expensive to change. But what we know absolutely from all of the work that's been done on looking at how we mitigate climate change and so on is that when you create a new piece of infrastructure or a new building, you really should be trying to aim for the highest possible performance, because that bit of infrastructure or that building is going to be locking you into a certain way of operating for the next 30, 40, 50 years.
Yeah, so this enables you to kind of make really important decisions correctly, where you know that the impact is going to be felt for years and years to come.
But, I mean, having said that, I wouldn't completely rule out the sort of retrofit aspect, because with these tools, you can enter whatever constraints you want. So you could enter the constraints of, say, all the bits of infrastructure or bits of buildings that are very difficult to change, the big, heavy bits of structure or whatever. And then you could tell the computer in a way that there are certain bits that are much easier to change, and then you can work through it. So there are still ways of doing it with existing bits of infrastructure. It's just a bit more challenging.
Yeah. Okay. I'd like to move on to your second example, but before we do, we're going to turn to Lou, who will tell us briefly what's coming up over the remainder of the Disruptive Innovation Festival. We'll be back right after this.
For a long time, we have been constructing, thinking that our environments, our built space needs to be rigid and needs to be static. Today, in a moment of acceleration in terms of where we live or how we work or how we communicate, we realize that our needs are changing with a very accelerated rhythm, and therefore our environments need to be able to adapt to those continuously changing needs. Traditionally, a building could not change at all. Traditionally, public space was a space that people could just meet and interact, but the rest that surrounded us was pretty much static and pretty much constructed in a way that consumed...
Hi, I'm Lou.
Right. Well, that obviously wasn't my colleague Lou, so you're no wiser than I am as to what's coming up next. That's a bit of a lie, because I do know what's coming up next, and I'll let you know a little bit later on in the session. In the meantime, we'll turn back to Michael, and we'll get your second example back up on the screen. And what this example I liked about this was that it kind of takes it to a bigger picture level. So we start to see what the potential of computational design can be.
Yeah.
I'll leave it to you.
Great. So this is one that we developed on the Sahara Forest Project. So the Sahara Forest Project involves bringing together a number of synergistic technologies in useful ways. And this diagram shows the main cluster of technologies. Those are the green icons. And then we're using what we have a lot of, sunlight, seawater, and carbon dioxide, to produce more of what we need, things like materials and food and oxygen. Now, the model that this was based on was an ecosystem model, where each of those technologies has its own inputs and outputs, and we try to connect those up so that every bit of underutilized resource from one part of the system is used by something else in the system. And that's very similar to an ecosystem where you've got loads of interdependent species. It's a zero-waste system in which the waste from one becomes the nutrient for something else. And this is very applicable to cities. Now, in conventional urban planning, we've tended to separate the different systems of food, energy, water, and waste. Those are the main ones. And the problem with separating those is that tends to lead to linear and wasteful ways of doing things. So we can learn a lot from applying these kind of ecosystem models to urban design. Now, one of the things that's quite challenging about these is that they can be quite complicated because you've got a lot of interconnections and is also dynamic. I think we should keep that in perspective. It's not that far beyond the kind of complexity we're used to. If you take the example of, say, the number of meals served in London every day. Roughly 20 million meals are served every day in London without any significant interruptions in supply or shortages and so on. And that's because that system is largely self-organizing. There's a lot of sort of feedback loops there, and that's evolved over time. So these, I would argue, are not any more complex than systems that we're already used to. But even so, what we did is we developed a design tool which is called CityCirc 1.0, which makes it easier to design these. So this allows you to enter a technology or a land use or a process, and you can enter the inputs and outputs, and then you can see ways of connecting these up. And at every point, the tool shows you anything that is underutilized. And that is a kind of prompt, really, for designers to think, okay, if something's underutilized, then that's a clue that we should add something to the system to create more value. And then what this tool allows you to do is to press play, and you can see how it operates. You can see if there are any problems. And this also allows you to test for resilience. So you could choose any one of those links and you could cut it. And if you get a wider system breakdown, then that indicates that you need to add something in terms of redundancy or duplication to make it more resilient, or sometimes add a form of buffering, commonly at some sort of form of storage. So this makes it easier to both design it and visualize it, so you can see what's going on. And by doing that, it makes it easier to design for this kind of complexity.
Yes. It makes me think of the idea of industrial symbiosis, the
Absolutely,
connecting of kind of multiple businesses or production plants, process plants, and making sure that all of the outputs and the inputs from all of those, up until now, completely distinct and separate streams of what we think of as waste, and being able to see it, visualize, as you say, how you can use each and every one of those to create a much more healthy system.
Yeah.
It's brilliant. And the idea of resiliency, I think, is also important. You mentioned it from an ecosystem perspective.
Yes.
And so great to see that this is being used. Where you use this for the Sahara Forest project,
That's
is that
right,
correct?
yes.
And it's available to designers to use, or have you used it in other applications?
Yes, we're now offering it as a design service, and we're just starting to apply it to certain urban models. So you may have seen some of the network diagrams that look a bit like food webs.
Yes.
For examples like Kalundborg, and there are one or two city examples like Hammarby Sjöstad in Stockholm. And this is basically the same sort of thing. So it's making it easier to design those sort of food webs that have a great deal of interconnectedness to them.
Super. So I've got some information now that's come to me about what sessions are coming up at the Disruptive Innovation Festival that would have been shared with you by Lou in that video. At 4 o'clock today, you can tune into Glue Like a Screw, that's a brilliant title, I think, where Eric Logtons from eCore will tell us about how two companies are creating reversible connections fit for disassembly. So there's something for the design-minded amongst you. And very exciting, you can watch the big video that was released today, which is called Hamilton on Reek, a story of food revolution from the favelas of Brazil. It's a beautifully shot documentary and just a wonderful story, I think. So when we finished here in the studio, there is plenty more for you to watch. We've had a comment that's come through. Someone was quite excited by something that you said a little bit earlier.
Right.
Kelly, who says that she is so glad to hear that designers don't simply go with what the computer produces, that we can't remove humans from the design process. There's not a question in there, but I thought it was nice to share that is something that people are I would presume designers out there might be a little bit nervous, frightened about what this technology means.
Yeah.
And so that idea that this is not a replacement for designers, but kind of is a tool in their arsenal,
Absolutely.
seems to be what you're hinting at.
It's a tool that should help us design much better buildings. So, if you take an example of, say, a housing development, this would make it easier to ensure that every single housing unit has a good amount of light, a good amount of access to external space, a generous amount of sunlight, and so on. Whereas, using more conventional means, you might end up with some of the housing units that are really rather poor in certain respects. So yeah, I think this is absolutely a tool rather than something that becomes our master, and we can still inject plenty of our imagination and creativity into it.
Do you think are there limits to this technology? We've seen that it can obviously handle a lot of kind of inputs and data.
Yeah.
I mean, are there computational limits, do you think, to this? We've talked about kind of its use and its applications, but how far do you think we can push it?
Well, I mean, in a way, this connects with what we already discussed, which is that in order for it to be a parameter to feed in, you need to be able to quantify it. And of course, there are certain qualitative aspects to architecture and cities that may never be able to be parametricized. Things like, how do you measure delight or a feeling of sort of comfort, or some of those sort of psychological and cultural factors I don't think we'll ever see factored into these because they're just too difficult.
Something that computers are just not designed
Yeah.
to kind of handle. We've had another question from the audience. I'm going to come back to it after we play another clip. This time the clip is coming from last year's Disruptive Innovation Festival, and it features John Maeder, who was a professor at MIT Media Lab for 12 years, and he is talking about how the rapid pace of computerized design is affecting designers these days. So let's see what John has to say.
So there's always going to be people who believe in classical design. There are always people who will need organizations, belongingness. They'll need design thinking. But computational design will continue to move at a rate that we all are having difficulty comprehending because it's powered by Moore's law thinking. Moore's law being the doubling of transistors every year to year and a half. So things are getting twice as good every year to year and a half, which is not normal.
You've got quite a lot of experience working at MIT's Media Lab in this area. And I'm particularly interested in what he said there about the fact that we, I guess as the general public, maybe designers in particular, are struggling to comprehend the acceleration of this technology. I mean, he even calls it not normal, which I suppose is probably true. Do you think that's true? Are designers kind of comprehending this? Are they aware of how powerful this could be a tool in their arsenal?
I think it's quite possible that computational power is accelerating faster than the rate at which designers sort of change their mindset. So I do agree with him there. But I don't see there's any sort of downside to that. And in actual fact, I'm really looking forward to being able to apply that model I showed, the City Circ 1.0, to a whole city, and it would look like an incredibly complex model, kind of pulsing and flowing all over the place. But I would absolutely love to do something as big and complex as that, and that's going to be easier and easier with increasing computational power.
We've had that question that I referred to from the audience was from Tace, who asked quite a provocative question, I think, which is how long until everything is computationally designed?
Well, I think we've addressed that already when we said that we won't get to that point. There'll be some things that never make it into these. So I don't think we should be too worried about these.
Which is, I think Peter will be happy to hear you say, because he says that we are regularly awestruck by architecture that was designed by humans, referencing the Taj Mahal, the Eiffel Tower, the Chicago Tribune building, the pyramids even. And he says that surely computers cannot compete with human ingenuity, which I think is exactly what you've said in this, is that there's kind of that human element just can't be replicated.
Indeed, and some of those examples that Peter mentioned, those are based on some really profound human instinct, trying to embody something, some kind of values or ideas or symbolism that will last for millennia. And that's not really something that comes into computational design. Computational design is really about sort of refining things. So that's not going to replace the big idea, which is at the heart of great architecture.
Does it change, though, the skills that architects and designers need? So you talked about in that first example that there was an engineer on your team who put together that model that you used.
Yeah.
Do you think that architects and designers, kind of in the future, as this becomes more and more prevalent, are going to have to develop the skills to do this themselves, to design these algorithms and run these computer simulations, or is there going to be perhaps a new profession of architectural computational designers as a kind of separate?
I think it's a bit of both. I mean, most of the students coming out of architecture schools now learn the basics of computational design, and then some of them choose to really specialize in that and just work on that 100%. So in my office, we do both. We have people that are good at computational design, but are kind of broader architects, as well as having one or two specialists that we use when we've got something really particular that we want to work on.
And do you think that it's going to be, well, it probably will be, I assume, used beyond architecture? So we've talked primarily about architectural examples today. Do you know of any examples where it's been used perhaps in product design or in kind of industrial design elements for those non-architects who are watching and are excited to try and get involved in this?
Oh, sure. It's being used in all aspects of design. I just tend to be more familiar with the architectural and urban and circular economy examples.
I'm going to return now to a topic that I know is kind of close to your heart and that you've referenced a few times already, which is the idea of biologically inspired design. We've talked about ecosystems, trying to kind of replicate what ecosystems do in their systems. You talked about Murray's law.
Okay.
When we talk about biologically inspired design, what is that exactly?
Yeah. It's really looking at how biology has solved certain problems and using those solutions to inspire innovations that suit human needs. So there are a lot of sort of functional challenges that biology has solved in very elegant ways. And then the characteristics of ecosystems, I would put those as slightly distinct because that's a sort of complex system model. And we can learn a lot of useful things from systems, from ecosystems. The way that they're based on very densely interconnected, independent species, they're very resilient, they run entirely on solar energy, they're zero waste, they're self-organizing, and so on. And a lot of those are useful pointers for us to look at when we're trying to think of how we need to redesign cities for a circular economy.
We've had someone who's been paying attention during the diff, clearly, because they're talking about a session that only happened last night, I think. He says that Steve Parkinson, in a session last night, he's an educator at Autodesk, was somewhat critical of the absence of computational design from schools and university curriculums and from design and engineering courses. Do you have any insight into that? Is that a problem that you've observed, or do you have any comment?
Well, it's interesting that some of the kind of Silicon Valley parents these days send their kids to old schools where they don't have access to computers at all. So I think, I'm not sure I'd entirely go along with that. And in my experience, nearly all architecture graduates that apply to my company have got a grounding in computational design. So I don't feel it's lacking from architectural education.
Would you say the same thing about biomimicry? Because I know that is something that, at least in my engineering curriculum, was not a part of it at all. I got a little bit of exposure to it in design school afterwards, but not a great deal.
Yeah.
Is that a kind of similar?
The uptake seems to be quite slow, actually. I thought architects would get much more excited about biomimicry much more quickly because there are just so many solutions that are directly equivalent to the kind of challenges that architects and engineers face. But for whatever reason, it seems to be rather slow. But on a more positive note, by far the biggest readership of my book, Biomimicry and Architecture, was among students, architecture students. So I think there's a sign there that people are going to get more and more interested in it.
Yes. I remember Janine Benyus, who is obviously kind of revered in the world of biomimicry, said that every design kind of process should have a biologist at the table.
Yes.
I think that certainly resonates today.
Yeah, absolutely. I mean, Janine has a wonderful turn of phrase and is very observant. And she makes the point that too often the involvement of a biologist or an ecologist in a design process is as someone to do the body count once the design has largely been finalized. And as she says, there's scope for a much more creative involvement by bringing the biologist or the ecologist in early on.
Brilliant. I think that's a good point to leave our discussion today. It's been fascinating to me, and I'm sure to the audience. But I want to just think for a minute about the quote that I borrowed from your earlier talk at the Disruptive Innovation Festival 4 years ago, where you talked about the fact that we may be kind of seeing the reawakening of human ingenuity. I think I came into this session expecting to feel like we were moving away from human ingenuity in the field of computational or digital ingenuity, and that was going to replace perhaps architects and designers. And you've well and truly put that thought to rest in my mind, and hopefully the designers out there are no longer concerned that that's the case. Before we leave you here at the Disruptive Innovation Festival, I wanted to remind all of you online that this is simply the end of the first week, or we're coming up to the end of the first week. There's more happening today. You've got a weekend ahead of you to catch up on all of the sessions that have happened in the past, and the DIF will be on for the next 2 weeks. So look forward to seeing you again in the future. Cheers for now.